we are using the Banker's algorithm, if the multiple instances of the resource, each resource type is available, then we can make use of the Banker's algorithm, because the in the last class I explained the resource allocation graph algorithm. That resource allocation graph algorithm we can make use of it only when the single instance of the resource is available. If multiple instances of the resources are available, then we cannot use the resource allocation algorithm. Hence we are moving on to one more algorithm called as the Banker's algorithm. So the efficiency of the Banker's algorithm is less when compared to the resource allocation graph, but the advantage is, if multiple instances of resources are available, then we can directly make use of the Banker's algorithm. Then what is the main requirement for the Banker's algorithm? Whenever the new process joins the system or enters the system, then the process must declare the maximum number of instances of each resource type it requires for its execution. Okay. So when the need is given by the each process, then when the process request for a resource, then before allocating the request, we are using the Banker's algorithm to check, after allocating the requested resources to the process, whether the system will be in the safe state or not. After allocation of the resources, if the system is in the safe state, then the resources are allocated. Otherwise the process makes to wait until the resources are released by other processes, then only the resources will be allocated to the requested process. Understood? So when the process gets all its resources, then it can complete its execution. After completion of its execution, it must return all the resources in a finite amount of time. So this is the main requirement for the Banker's algorithm. So then how we can go for our, what will be the implementation details? So here for the implementation purpose, we require or we define 4 data structures. Those are, one is available, second one is maximum, third one is the allocation, and fourth one is the need. So these are the 4 data structures we need for the Banker's algorithm. So now we'll consider n is the number of processes available, and or number of processes exist in the system, and m is the number of resource types. Next, one data structure is available. It indicates the number of available resources of of each instance, or we can say that number of available resources, and that is represented by a vector of length m, where m is the number of resource types. Now let us consider that we have 3 different resource types. What are those? CPU one is one resource type, another one is the memory, other one is, let us consider, the IO device. So these are the 3 resource types. Then what will be the m? M is equal to 3. It is indicates the number of resource types, so it is equal to 3. Then available is the vector of length m. If available j is equal to k, then there are k instances of resource type rj is available. Means what? So as I said, 3 resource types are available: CPU, memory, and the IO device. So if 4 CPUs are available, then available of j is equal to k. K indicates there are k instances of resource type rj. K is equal to 4. 4 types of 4 CPUs are available, means k is equal to 4. And how many instances now here? There are 4 instances of resource type CPU. Understood? So here k is equal to 4 and resource type is a CPU, that is equal to rj. Understood all of you? Understood? Any doubt in this? Available indicates it is a vector of length m. If available of j is equal to k, then it indicates that there are k instances of resource type rj available. Like that, we will consider the IO devices like the printer and scanner. So how many are there? 2. 2 instances of resource type IO device is available, like that. Understood? Next, one more data structure is maximum. So this is a matrix of type n into m. If max of ij is equal to k, then process pi may request at most k instances of resource type rj. So as I said previously, 3 types of resources are available: CPU, memory and IO device. So among these 3, the process requires all 3. Then how many instances of each resource the process requires? So now the process P1 requires 2 CPUs, 1 memory and 2 IO devices. So it requires 2 CPU, 1 memory type. So it may be the tape drive or the magnetic drive, and the 2 IO devices, scanner and printer. So what is the maximum requirement for the process P1 to complete its execution? It requires 2 CPU, 1 memory type and 2 IO devices. So then the value becomes 212. 2 is CPU, 1 is the memory and 2 are the IO devices. So these are the maximum resources the process P1 required for its execution. Understood? Now allocation is, once again it is, we are representing the allocation in terms of n by m matrix. If allocation of ij is equal to k, then pi is currently allocated k instances of rj. So as I said, pi the process P1 requires 2 CPU, 1 memory and 2 IO devices. Among those, only 1 CPU is allocated, 1 memory is allocated and 1 IO device is allocated. Then what the allocation matrix equals to? 1 comma 1 comma 1. So maximum required is 212, but the allocated is 111. So that is the allocation given, are that those are the resources allocated to the process P1. Understood? Now the need. So how we are calculating the need? Need is equal to maximum minus allocation. What is the maximum resources the process P1 requires? Maximum resources required is 212 and allocated is 111. Then the remaining need, how we are calculating? By using the maximum required minus allocated resources. So maximum is 212 minus allocation is 111. Then what is the remaining need for the process? It is 101. Means the process requires one more CPU and one more IO device to complete its execution. Understood? Any doubt in these data structures? Available means maximum number of resources available, and for each resource we have multiple instances. Next, maximum is the maximum number of resources of each type required for the process to complete its execution. Among the maximum, currently the process is allocated with some set of resources, and that is represented by allocation. After that, we are calculating the need. Need is the maximum minus allocation. So maximum is maximum resources required by the process. Allocation means currently allocated resources. If we substitute the allocated resources from the maximum resources, we are getting the need of resources for the process P1. Understood? Any doubt in these data structures? If not, I'll move on to the next topic. Any doubt? So for the implementation of the Banker's algorithm, we require these 4 types of resources. Okay, next we'll move on to the next slide. So next we are going to see the safety algorithm and also the resource request algorithm. So first one is the safety algorithm. So Banker's algorithm consisting of these 2 algorithms. One is the safety algorithm and the other one is the resource request algorithm. So before the resources to be allocated to the request process, the Banker's algorithm executes or runs these 2 algorithms. One is the safety algorithm and other one is the resource request algorithm to find whether after allocation of the resources the system will be in the safe state or not, and whether the requested resources to be allocated to the requested process or not. To know about these two, we are using the or running the safety algorithm as well as the resource request algorithm. First we will see the safety algorithm, next we will move on to the resource request algorithm. So now, to find out whether or not the system is in a safe state or not, we are using the safety algorithm. Means to know whether the system will be in the safe state or not, then we are running the safety algorithm. So in this algorithm, two vectors are defined. One is the work and other one is the vectors. Other one is the finish. So work and finish are the two vectors of length m and n. So initially we are initializing work is equal to available. Work is equal to available. Available means available resources, and finish of I is equal to false for I is equal to 0, 1 up to n minus 1. So up to n minus 1 means we are considering the number 0 to 1, where finish of I we are assuming that the process not yet finished their execution. Means if we are initializing that to false, it indicates that no process is completed its execution, all are in the ready state and all are waiting for the execution, right? So that is indicated by finish of I is equal to false. Finish of I is equal to false means no process in the system is not completed its execution. Okay, work is equal to available indicates that work is equal to available resources. So okay, now first in the first step initialization is over, right? Work is equal to available and finish of I is equal to false. Next we are finding an I such that both finish of I is equal to false and need of I is less than or equal to work. What it indicates? We are finding a process in a queue such that that process has not yet completed its execution and the need of that process is less than or equal to the available resources. Understood? So finish of I is equal to false indicates that we are finding a or we are selecting a process in such a way that that process has not yet completed its execution and the need for that process or need of resources for that process is less than or equal to the available resources. Understood? So if these two conditions satisfies, then the resources will be allocated to the requested process and we assumes that the process has completed its execution. After process completes its execution, then it releases the resources, that is work is equal to work plus allocation and finish of I is equal to true. So what it indicates? Work is equal to work plus allocation indicates that after the process completes its execution, it releases the resources. So finish of I is set to true. It indicates that the process has completed its execution and released the resources. And next, so if that condition is not true, then we'll move on. We will move back and we'll consider one more process. Understood? Any doubt in this? Okay. Next, the fourth step is if finish of I is equal to true for all I, then the system is in the safe state. So what it indicates? Suppose in the system we have three processes P1, P2, P3. Then if finish of I is equal to true for all three, for all I, then the system is in the safe state. Means if we are allocating the resources to all the processes P1, P2 and P3 and all have completed their execution, then we'll say that the system is in the safe state. Understood this algorithm? Any doubt in this algorithm? Okay, so here we are using two vectors work and finish of length m and n, and we are initializing work is equal to available, means available resources are initialized and we initialize finish of I is equal to false, means no process has completed its execution, all are in the ready queue for and ready for execution. Now we are finding an I such that finish of I is equal to false, means we are finding or selecting the process such that that process has not completed its execution and that process need is less than or equal to the available resources. So then the resources will be allocated to that process and the process completes its execution. After completing its execution, it releases the resources, and that is work is equal to work plus allocation. So we'll take back the resources, then once again that becomes the available resources, and finish of I is set to true. Set to true means that a process has completed its execution. Understood? So if those two are true, then we'll select one more process. Okay, that is completed. Process P1 is complete. Let us consider that P1 is completed. Then in this go to step 2, means we'll go back and we'll select the next process, and this repeats until all the processes in the system completes their execution. That is finish of I is equal to true for all I, then the system is in the safe state. So if all are completed and no process is in the deadlock situation, then we say that the system is in the safe state. Understood? Any doubt in this algorithm? Because this algorithm is very important while solving the problems. Okay, so if no doubt, then I'll move on to the next algorithm, that is called as resource request algorithm. This is also one of the algorithm in the banker's algorithm. So two algorithms are there. One is the safety algorithm and the other one is the resource request algorithm. Understood? Okay, so we will see the other one is the resource request algorithm. So this algorithm determines if the requested requests can be safely granted to the requested process or not. By using the safety algorithm, we will determine whether the system will be in the safe state or not, and by using the resource request algorithm, we will determine whether the request can be safely granted or not. So if can be granted, so that the system should be in the safe state. So by considering that, we will decide whether the requested resources to be allocated to the requested process or not. So we will see this algorithm. So we have one variable called as the request. So here that is also a vector for process Pi. Okay, so request of I is equal to request vector for process Pi. If request of j is equal to k, then process Pi wants k instances of resource type Rj. Now let us consider the resource type as CPU. That is Rj is equal to CPU, and the request of j is equal to k, then process Pi wants k instances of resource type. Let us consider that 4 CPUs are available. The resource type Rj is equal to CPU, and how many instances are available? 4 instances are available. Among 4, the process Pi is requesting one CPU. Understood? So the process Pi is requesting one CPU. Then first condition is we are checking whether the request by the process is less than or equal to the need. Suppose initially the process Pi given the information that it requires minimum it requires 3 CPU to complete its execution. Understood? So currently it is holding 1 and it is requesting for one more resource or one more CPU. Okay, so now what is the need? So total required is 3. Currently 1 is already allocated. Then what is the need? It requires 2 more. So the need is 2 and it is requesting only 1. Now we will check, that is if request is less than or equal to need. Yes, request is 1 and that is less than or equal to 2, right? That condition satisfies. It is true. Hence, the requested resources is less than the need. Then we'll move on to the next step. That is, we'll go to step 2. In step 2, we'll check whether the request is less than or equal to available. How many are available? 5 are available. Among 5, process PI needs 3. Among 3, 1 is already allocated. Then how many are available? 4 are available. So request is less than available. So it requests 1, but how many are available? 4 are available. So that condition is also true. Then the process PI gets the CPU, or the CPU is allocated to the requested process PI. So after allocation of the CPU to the process, will pretend that allocated requested resources to PI by modifying the states as follows. Now available is equal to available minus a request. Why? Because we are already allocated. One is already allocated first. In the next case, it is requested for one more CPU, and that CPU is also allocated. Why? The first two conditions satisfy, because the request is less than or equal to need and the request is also less than or equal to available. So hence we are allocating the requested CPU to the process. After allocation, we calculate the available, allocation and also the need. Now what is the available? Available is equal to available minus request. How many are available? 4 minus 1. Now the available becomes 3, and allocation is equal to allocation plus request. 1 is previously allocated and request is plus 1. So 1 plus 1, allocation becomes 2, and need is equal to need minus request. What was the need? Before it was 3. Out of 3, 1 is already allocated, and the present need is 2. Out of 2, 1 is requested and that is allocated. Then this becomes 2 minus 1. So need becomes 2 minus 1, that is the need. So then how many are available? Available is 4 minus 1, it is equal to 3, and allocation is 1 plus 1, because 1 is already allocated and request is now currently requested, and that is also going to be allocated, and hence it is allocation plus request is equal to allocations. Now allocation becomes 2 and need is need minus request. Need was 2 minus request is 1, then the currently need becomes 1. So after calculating this, if the system results in a safe state, then the resources are allocated to PI. Understood? So if after calculation of these available, allocation, need, then we'll check whether the system will be in the safe state or not. If the system is in the safe state, then immediately the resources are allocated to the requested process PI. If it results in a unsafe state, means once the process request for the resources, if the resources allocated leads to the unsafe state, then the resources will not be allocated and will make the PI, the process PI, to wait until the resources are released by other processes, or until the whole resource allocation state is restored. So this is called as the resource request algorithm for the process PI. Understood? Any doubt in this? Any doubt in this? Any doubt? If not, then I'll move on to the problem. So as I said, it is an important algorithm, Banker's algorithm. So normally in all the question papers, one problem will be asked on Banker's algorithm. Calculate the safe sequence or find the safe sequence for the given scenario by using the safety algorithm and the resource request algorithm. So if you understood these two algorithms, safety algorithm, then the resource request algorithm, then we can move on to the solving of the problems. Now we'll consider any doubt on resource request algorithm or the safety algorithm? Any doubt? If not, we'll see the problem. Now let us consider that in a system we have 5 processes. In a system, we have 5 processes, process P0, P1, P2, P3, P4. So today I will explain the scenario, and tomorrow I will solve the problem in detail by through the use of the safety algorithm and the resource algorithm, resource relocation algorithm, resource request algorithm. So I will use those two and solve the problem tomorrow. But today we will calculate how to calculate the need matrix. I will explain. Okay. Now let us consider the example of a system which consisting of 5 processes P0, P1, P2, P3, P4. P0 to P4, and how many instances are available. So first we will consider how many resources are available, and for each resource how many instances are available. So in a system 3 resources are available. 3 resources are A, B, C. So 3 resources are available A, B, C, and how many instances of each resource type is available? 10 instances of resource A, okay, 10 instances of resource A, 5 instances of resource B, and 7 instances of resource 3. Now we will see the maximum and the allocation and what are the available resources. So for P0, maximum need is 753. So there is a difference here, 753, okay, ABC 753. Here it is 753 are the maximum requirement for the P0, means P0 requires 7 instances of resource type A, 5 instances of B, and 3 instances of C, and out of 753 0 instance is allocated at present, and 1 instance of resource B is allocated, and 0 instance of resource C is allocated. Understood? Here we have 3 resources A, B, C, and out of A, B, C resources 10 instances of A, 5 instances of B, and 7 instances of resource C is available. Out of 10, 5 and 7, what are the requirements for each process? Let us consider. So P0 requires a maximum of 753, means P0 requires 7 instances of resource A, 5 instances of resource B, and 3 instances of resource C, and out of 753 only 010 is allocated to process P0, means only the one instance of process B is allocated at present. Similarly for P2, what is the maximum requirement for P1? It is 322, means 3 instances of A, 2 instances of B, 2 instances of C. Out of 322 only the 2 instance of resource type A is allocated, and for P2 what is the maximum requirement? 9 instances of A, 0 instances of B, and 2 instances of 3. Out of 902 only 302 are allocated to process P2. Understood? Out of 902 only 302, means 3 instances of A is allocated, 0 instance of B, and 2 instances of resource type 2 is allocated. Similarly for P3, what is the maximum requirement? Maximum requirement is 222. So means it requires 2 instances of A, 2 instances of B, 2 instances of C. Out of 222 only 211 are allocated. 211 are allocated means 2 instances of A, 1 instance of B, and 1 instance of C is allocated to P3. Similarly for P4, 433 is the maximum requirement for P4, but out of 433 only 002 are currently allocated. And what are the available resources? The available resources are 332. So 3 instances of A, 3 instances of B, and 2 instances of C are available. Among the available 332, we have to allocate to all the processes P0 to P4, and we have to keep the system is in the safe state. Then how we can be allocated? So before allocation we need to calculate the need matrix. Then how to calculate the need matrix? Need matrix is calculated by using the maximum minus allocation. So by using maximum minus allocation, we are calculating the need matrix. So for P0, what is the maximum allocation? So maximum requirement for P naught is 753. So maximum requirement for P naught is 753. Okay, so maximum is 753, and out of 753, 0, 1, 0 is allocated. Now calculate the need matrix by subtracting the allocation by maximum. Maximum minus allocation gives the need matrix, that is 3 minus 0 it is 3, 5 minus 1 4, and 7 minus 0 it is 7. So the need value is 743. How we got 743? By subtracting 010 by 753, that is 753 minus 010. So 753 minus 010 gives the value 743 for P naught. So that is the need matrix for P naught. Similarly, we can calculate it for P1. So for P1, what is the maximum requirement? Maximum requirement is 322, but the allocated is 200. Now calculate the need matrix, that is maximum minus allocation. It is equal to 2 minus 0 2, 2 minus 0 it is 2, 3 minus 2 1. So hence it is equal to 122 for P1. Similarly calculate it for P2. What is the maximum requirement for P2? It is 902. And what is the current allocation? Current allocation is 302. Now what is the need matrix? 2 minus 2 it is 0, 0 minus 0, 9 minus 3 it is 6. So that is the value for P2, that is 600 is the need value or the need of resources for P2. Similarly calculate it for P3. For P3, what is the maximum requirement? Maximum requirement is 222, and currently allocated is 211. Now what is the need value? 2 minus 1, 2 minus 1 1, 2 minus 2 0. So now for P3, what is the need? It is 0 1 1. Similarly calculate it for P4. So for P4, what is the maximum requirement? It is 433. 433 indicates 4 instances of resource A, 3 instances of resource B, and 3 instances of resource C, and currently allocated is 002. Now what is the requirement? It is 3 minus 2 1, 3 minus 0 3, and 4 minus 0 is 4. So now the need is 431. Understood? So how to calculate the need value for each process, and this gives the need matrix. With class.